failure is not an average. So you don't say that, right? I failed, you say I failed in this course. You don't say that I failed in the semester. If you have 8 courses and you fail only in one, you fail in one course, you fail locally. Well, some people have the talent to fail globally, but generally you fail locally, right? You fail one by one. And then what happens? Again, same thing. You fail in this semester, then next semester you have an additional load to study a lot. The chances are that you will fail in more because you have additional load. Same process happens, right? So failure is a local phenomena, and that is where, that leads to my next point, reinforcing bars or fibers are local strengthening agents. Fibers especially are local strengthening agents. I was telling somebody, what happens is micro cracks will have in concrete. What a fiber, a steel fiber will do is to carry the load, disperse the load so that this crack will not open and widen further. You will have an initial crack, but the fibers will start to carry the load instead of your concrete carrying the load. So understand a very important point, failure is always local. Failure is never global, failure is local. And several localized failures coalesce to give what we perceive to be a global failure. And you cannot design for a global failure, therefore you have to design for a local failure. Local failure meaning controlling things at the local scale. What is local as far as concrete is concerned? If I am looking at concrete with my naked eye, what is local? Aggregates and cement paste. If I am looking at cement paste under a microscope, what is local? CSH and calcium hydroxide. If I am looking at CSH further under transmission electron microscope, what is local? The layers of CSH, right? The definitions of local and global changes. For the government sitting in Delhi, whole of Karnataka is local, right? For somebody in Bangalore, Mangalore is local. Somebody in Mangalore, this little part is local, right? Local and global depends on how you look at it. But failure always is local. So the more detail you can go in, the better you can capture the reasons for failure. Nobody captures the reasons for failure. You will see a lot of consultants coming and walking and looking at a bridge deck and explaining how it failed. I mean, they're all hypothesizing, and because they know a lot of things from history, they might be correct most of the time. But if you don't know what it is, you can't just go and say, oh, this is how it failed. Because failures are always local. Okay. Size effect on compressive strength, you will know that the larger you make your specimen, the weaker it gets. So your best option is to make a real tiny cube, right? What is the reason for that? Why do you have a 300 mm cylinder, 300 mm cube showing you a lower strength than a 150 mm cube, showing a lower strength than a 75 mm cube? Material defects. When you make a larger and larger materials, the chances that you have defects in that material is larger. If I can theoretically take atoms and connect atoms together, sit down and connect all the atoms together properly, I should have no size effect at all. I should have the highest strength for that case, but that doesn't happen. Water cement ratio on strength, we'll put it, elasticity, I told you about that. And again, the idea that as is the extension, so is the force, not the other way. Okay? As is the extension, strain is fundamental, stress is secondary. You don't measure a stress, the material actually feels a strain, it responds as a stress, and you try to measure that stress because of an imposed strain. Even when I am saying I am applying a load on this, I am not applying a load on this floor, because of my standing here, the floor is deforming, and because the floor has certain rigidity, it wants to oppose the deformation. That is the stress that you see, right? Opposing the deformation is the cause of stress, not applying stress. Okay, so just some basic ideas so that you don't mess it up anywhere. Again, you would have seen these pictures at a very low. Even with starting, you have some micro cracks. Micro cracks start to expand. They became connected cracks, and they fail with a lot of these connections. And you've seen these pictures over and over again. Stress strain curve of concrete. All of you know secant modulus, tangent modulus, chord modulus, all the simple boring stuff. composite models for concrete. I'll give you these notes. These are just mathematical comforts that you can have. Refined composite models. You can do a lot of nice models for concrete. Some of them works well. Okay, axial and lateral response. So load, axial strain, you get this. This is your proportionality limit, so look at how much of nonlinearity you have, right? And this is your lateral strain. So lateral strain over longitudinal strain at the same stress level will give you your Poisson's ratio as long as you are the linear elastic range. So somewhere here, that's your Poisson's ratio. Volumetric strain, I talked about strain being in volumes. When you measure strain, you measure a length change. You take it to the lab, you put it under a extension comparator, and then measure the length change. But in real life, concrete is a three-dimensional material. And like I said, when you push, you have strains in the other directions also. Therefore, volumetric strains are more important. And volumetric strain is a sum of the strains in three orthogonal directions, not a product of the strains. So if you measure strains in x, y, and z directions, volumetric strain is the total additive value of all the three strains, because volumetric strain is very important in shrinkage in real life, right? It's shrinking in all directions. So you have to look at volumetric shrinkage strain rather than linear shrinkage strain, because depending on the surface area to volume ratio, shrinkage in all directions might not be the same. So you take a linear strain, you might get some kind of an indication, but you will have strains in other directions also. Envelope of tension compression, testing for tension. I'll do a quick bit of fracture mechanics for concrete. So basically what we do is all the time what we rely, again, I'm not trying to say one method is better than the other. So there are people who are continuum lovers and people who are fracture lovers. And there's always a conflict between the continuum guys and the fracture guys. The continuum guys say that this is all a continuum, you can apply the uniform laws of physics to all of this and get it done, and which happens most of the time. The fracture guys say that no, failure is local. If failure is local, you have to account for local failure, and the local failure will have to dictate what stresses you have. Sometimes they converge, sometimes they diverge dramatically. There are certain cases, for example, if you do an aerospace composite design for an aircraft that's flying up, for a rocket, you always do a fracture-based design, because a failure is local and that failure can cost very much. If you're doing a bridge deck or a road, forget it, cracks, move on. We know concrete cracks. I have a lot of these admixture companies manufacturing crack sealants. All these companies manufacturing hundreds of products that you can throw into all these cracks and seal the cracks and all of that. So move on, we wouldn't do it. Again, it's a question of what the criticality of your problem is. Sometimes you want it to be a little bit more involved. So if you're doing fracture mechanics, so typically when you say, I apply a stress, when the stress exceeds the strength, the material fails. Very simple. Stress, strength, stress, strength. Whereas when you get to fracture mechanics, you say, no, I apply a stress, I have no idea of strength, because I cannot say a strength, because strength changes from point to point. So when I say that there is a certain strength, it applies to only that point. When you exceed that point, exceed that strength at that point, I fail there. So the global strength has no meaning. What you have is a material toughness. Toughness is a capacity to absorb energy. That is what is more important, quantity, and then size of the defect. The larger defect, faster failure, smaller defect. So you have now a relationship between these three things when you do fracture mechanics. The idea that crack size, you start with a certain design strength, and this is very common in concrete. You start with a certain design strength. After some time, you get here, like your director was saying on the first day. After some time, you get a lot of cracks increase, and your strength drops down. But in some of the buildings here, this happened right here. That was what he was saying, right? Even before the building was open, it started to crack. So sometimes that happens. But then under service, it cracks, and you figure out that, okay, I can afford, this is my highest expected load, and I can therefore expect that kind of a crack. Anything more than that, I will have in service failure. What happens? You go seal the crack, fill the crack, repair the crack, try to take it back to some point here, crack goes. So you have this back and forth play here until you decide I don't use the structure anymore, I can demolish. So it's a function of how big the crack size is and what you think is required for failure. So to give you an idea, if I take a circle, if I take an ellipse, and I pull this thing in tension, this is the local stress, that's a far field stress. See here, local stress is much higher than the far field stress. If I have a really narrow crack, a very sharp crack with the tip of the crack being just a point with almost a zero radius, my stress at that tip will be infinity. Theoretically infinity. Now infinity also is a mathematical construct. Infinity just means very high compared to everything else, things that are orders of magnitude high. You can do all of these and you can prove that 3 is the optimal stress concentration factor that you can say. That's what I was saying. If I have a circular crack, my regions around the crack will see 3 times the stress I apply. Okay? So think about it. If I have a crack in the form of a circle in a concrete specimen, and if I apply a tensile stress, the crack will see 3 times the stress, which means even if you are 3 times lower than the maximum strength, you have a chance of failure. Okay? One simple reason why when we were doing our ultimate strength design, you always use a factor of safety of 2 to 3, right? Because you want to avoid that scenario. But now we do limit state design, you have a lot of statistical increase in loads and reduction in strength that you do. You don't have to do that. Okay, stress concentration, you don't have to do all of that. Greatest energy balance, we'll skip all of that. Basically the concept. Now, in concrete, you have something called a fracture process zone. Okay, this is a very nice concept. This is like the crack needs energy to dry. Right? You have a crack in the material, so that's a micro crack, whatever. The crack has to dry. So think of a bridge there, or think of a pavement, think of a structure, whatever structure that you want. Load is constantly applied, there's always load in the structure. Right? And initially say you have a crack. The load is nothing but the driving energy for the crack. Right? Load or force multiplied by the distance that the force moves the point that you're considering gives you energy or work. That energy is nothing but what we call the strain energy stored in the material, right? That is strain energy, internal strain energy. And the release of that internal strain energy happens when it cracks. So if I take a piece of paper, I don't know if I can tear this here. Yeah. So if I tear this piece of paper, okay, listen. If you close your eyes, you still know I'm tearing this paper, right? How? You heard the sound. What is happening? The internal strain energy stored in this paper is being released as heat and sound. There's actually a slight increase in temperature when I do this here. We can't measure it because it's so small, but basically you can hear the internal strain energy stored is being released as heat and sound. That is what is happening. You know the principle of conservation of energy. Energy cannot be created nor destroyed. Which means if this energy is being released outside, the material should have had that energy stored. Right? So anytime you load a material, remember, if this building, if you have concrete columns in this building and there is load on it, they are storing the energy because of the load. And they are in the shape that you see them and they are not failing because they have the capacity to store that energy. Once the capacity to store energy is exceeded, energy has to be released in some form, and typically that is why when things explode and fail, you hear a noise, you hear a sound, because it is the internal strain energy that is stored in the form of internal work that's being released. Okay? So when the crack drives, when the crack goes, and so again that's a global thing. Think of local. You have a crack. Under load, the crack is propagating. The crack is propagating, but the crack doesn't have a highway. The crack has to spend energy. The crack is like a cab driver in Bombay trying to squeeze his car in between two other cars and pushing those two cars to the front and back, right? The crack is finding a space to go through. Crack growth and crack also follows all the energy principles that we talked about. The most important energy principle being nature is designed to be lazy. That's the most important energy principle. Okay, if you don't want to really read the law of thermodynamics, this is a simple explanation of the law of thermodynamics. Everything is designed to be lazy. You follow the path of least resistance. Cracks also do that. So when they go through, when they see an aggregate, a really hard aggregate, it says, I don't have the power to break this guy, but I can go around. Right? Yeah, I may have to spend, like you have traffic jams and you divert. I may have to go more, but that is a good thing for you as a concrete engineer because you have made that crack lose its energy. Right? Energy is a finite quantity. It is coming from the internal stored energy. Now you made it dissipate the internal stored energy. Now it has to work hard to create that energy to crack further, which means you have artificially blunted a crack. You see that? So crack needs energy to go through, and when it goes through, it distributes its energy around. So when it distributes energy around, what happens? You have local strains. I'll show you some nice pictures where local strains can be captured. You have localized strains. All of you get the point? When a crack goes through a concrete, it has to move, which means you have localized displacement of those points. Okay, so you create a zone called the fracture process zone in concrete where you have very high localized strains. And if I follow the path of localized strains, if I have a very strong instrument that can follow the path of localized strains, I can predict where the crack is going even before the crack has gone there. Is that not a great tool to predict the life of a structure? I'll show you some examples. So now what you're doing is, I know this is cracking, so you have to intentionally put a notch to introduce cracking. But once you know that, you know where the crack is going through localized strain intensities even before the strain differences have translated into cracks. Okay? So that zone where you have a high intensity strain is called the fracture process zone, which just means the process of fracture is happening in that zone. Okay, it is an indication that something is happening in that zone. Okay, you look at temperature differences to see if something is about to happen. Have you heard about the volcano that is constantly erupting in Hawaii now? You've seen pictures of that in newspaper. So they do thermal imaging to find out under which part the lava is the hottest so that it will come out. Right? What they want is to predict which part of this volcano. Now, compared to them, we have a very simple problem. You know which bridge you want to look at. They don't know where they have to look at. So they have to do aerial imaging of a very large area and do a lot of image analysis to figure out what is the most likely location where it will crack, because they have to evacuate people. You can't say everybody 15-mile radius of this place evacuate. Right? You can't do that. You have to find out where you have to ask the people to evacuate so that you carefully do it. So let me show you those pictures. So here is a beam with a small notch. You're applying a load. And so here is a crack. Right? Your crack is going here, crack has blown all the way here. So you can have very sophisticated image analysis cameras, do a lot of mathematical calculations. We'll leave all of that, and I'll show you a few pictures. This is the center part. 0, 0 is the tip of the notch. 0, 0 is this point. Okay? Tip of the notch right there where the crack will start. You see at different times extremely high strain intensity, and you can under different loads. So this is under a load at that point, close to peak. To see how the crack has propagated, what is the intensity of strains around it. Okay, I'll show you here. There's another picture of how the crack is growing with different times. See if I have one more picture. So that's how you can do crack extension, and it's kind of a laboratory technique. There are some companies trying to bring in sophisticated instrumentation that you can put on ready-made platforms to investigate real-life structures for crack propagation, crack extension. Some years away, but a nice tool to actually predict where your structure is going to fail from the idea of localized strain index. Okay. Any questions on this? That's pretty much the mechanical properties that we will cover. Again, very quick overview relating what's happening at the microstructure level to what happens in the larger scale. Any questions?
In high strength concrete, the crack passes through the aggregate.
Very high strength concrete, yes. So the base is much stronger than the aggregate, yes. The crack passes through the aggregate. Other questions? Okay. So, the last topic, quickly on durability. Okay, I have a bunch of different things on durability. What do you want me to cover more? There is alkali aggregate reaction, there is sulfate attack, there is corrosion, there is, what do you want? Huh? Corrosion? Corrosion? Everybody wants corrosion? Really? Why? It's not a concrete problem, it's a steel problem. And I'm not teaching you steel. Huh? Huh? So sulfate attack now. Everybody wants everything, right? Come to a, okay, if overwhelmingly it's corrosion, we'll do corrosion. If overwhelmingly it's sulfate attack, what I'll do is okay. Corrosion for everyone? No? Huh? Steel? I didn't get you. Steel's concrete, yes. Yeah, steel's concrete during corrosion, yes. So it's a concrete problem. Well, basically it's a concrete problem also. So we'll do corrosion. What I'll do is anybody who wants sulfate attack, anybody who has other questions of sulfate attack, we'll do at the end. Okay? So I'll do corrosion because apparently, actually also, in terms of the scale of the problem, in terms of the intensity of the problem, in terms of how much money is being drained out of everyone's pocket, including all the taxpayers, corrosion becomes a very important problem. So I'll give you all these notes if you want, and then I think there will be a PDF of all these that will be in the GYAN website apparently. So you can look at all these, so you will lose nothing. So we'll start with corrosion. Okay. It's basically an electrochemical problem. It's a dissimilar metal in a solution issue. Concrete is being a pool of solution as far as metal is concerned. Normally metals in any other environments will have to deal with whatever is the local corroding species. Now coming to concrete, steel will have to see every possible type of species in, and you'll have to learn how to deal with it. Okay. So again, all of you know the basic issues of corrosion, of what happens with anodic and cathodic areas. You remember, right? Anode gains electrons, cathode loses electrons. If you know that, that's pretty much what's in corrosion. Now the specifics are very different. We still have not been able to solve corrosion problems because of several reasons. So let's do the big picture, the 30,000 feet view first. Why are we not able to solve the problem of corrosion of steel and concrete? If somebody asks you this question, as civil engineers, as somebody who has seen corrosion all over, what will be your answer? We have spent so much of money in research. Every institute that you can see, somebody is doing research in corrosion. Whether it's good, bad, ugly, I don't know. Somebody is doing research on corrosion. Why haven't we even come closer to completely understanding the problem? Let's forget about solving it. Why is that so? Or what is that is so important in corrosion that everybody seems to trip on it at the last minute? What do you think causes corrosion? Porosity in concrete is one reason, okay? Now, is there a way to control the porosity in concrete completely? No, we can make it better. We did over the last 4 days, we talked about how to make it better. What else? Where does porosity come from? No, where does porosity come from? Come from? From water, lack of filling in the space. Okay. If that is the only reason for porosity, if space not being filled efficiently is the only reason for corrosion, I gave you enough tools, and I'm not the first one to say that. A lot of people have given enough tools to fill the space efficiently. Why are we still having corrosion? Maintenance, but even before that something has happened. Passive coating. You have to think even more back before the structure is being built. Huh? Environment. We keep blaming everything that you can say environmental. You keep blaming things that you have no control over. You say I want to have a concrete with no porosity. Are you ever going to get it? No. You blame the environment. Are you going to control the environment in this place? No. Go back. What is that you can do? You don't protect the steel enough. Go back some more. You don't design the structures properly in the first place. Structural design, the structural designer doesn't talk to the architect, doesn't talk to the structural designer doesn't talk to the concrete engineer doesn't talk to the contractor in the field. Finally, they talk only when they have to point fingers at each other. This has to start from design. I cannot design a marine structure the same way as I design a structure in the desert. Period. I cannot. I've been telling this to everybody that I can see. You cannot be designing buildings like this in this place with such heavy rainfall where everything is exposed. When you have lunch and when it's raining, you can see water falling through the face of all these columns in this building. You cannot design like that and then expect not to have corrosion. Now, if the idea is to give all the contractors more business, then I completely understand it. And that is maybe a fair thing to do because people need business. That's okay. Then don't complain about corrosion. Right? This is how we know medical companies in the US. Very classic example. So we all have insurance, right? So we don't go to doctor. If you don't have insurance, you better die. There is nothing else you can do because I mean, if you